Optoelectronic devices are devices which converts electricity into light or light into electricity. These are various type of optoelectronic devices. LED, which converts electricity into light. Photodetectors are devices which detects light. So actually photodetectors converts light into electricity. Photodiode, phototransistor, pin photodiode, these are some of the photodetectors. The first one, LED, the light emitting diode. It is a heavily doped PN junction diode. Usually LEDs are forward biased. So when we connect this in a circuit, LED should be forward biased. So there is a series resistance and it is connected to a battery. The positive of the battery is connected to the positive of the light emitting diode. So it is always forward biased. Now the wavelength of the emission, LED emits light when we give electricity, when we give voltage to an LED. So the light emitted from an LED depends on the type of the material. Actually, it depends on the band gap of the material. So the semiconductor materials used for the construction of LED should have a very wide band gap. And the wavelength of emission depends on the band gap. So Eg is the band gap, which is equal to h into nu. And nu is c by lambda. So we'll get wavelength of emission from this equation. Now LED is used for various electronic applications and it has many advantages like low power consumption, longer lifetime, better physical robustness and smaller size. This is a typical IV characteristic of an LED, and this particular plot is for gallium arsenide phosphide. Now photodetectors, so which actually converts light into electricity. And it is used in, so photodetectors are mainly used in optical communication systems. And there are three types, depending on the mode of operation, there are in general three type of photodetectors. One is photoemissive, then photoconductive and photovoltaic. Photodetectors, when we construct photodetectors, it should have high sensitivity, high reliability, wide band gap and low noise and also low cost. Now we can see different type of photodetectors. The first one, photodiode. Photodiode is a reverse biased PN junction. So it is also known as the junction photodiode. The junction photodiode is a photodetector which is always reverse biased. In a junction photodiode, we have a thin P layer on an N substrate. And when we apply a reverse bias to the junction photodiode, which means the P region should be connected to the negative of the battery. In the P region, holes are the majority carriers. So that is given a negative polarity. So reverse bias. So the given reverse bias is in effect a forward bias to the minority carriers. Because in the P region, electrons are the minority carriers. So what happens with the reverse bias, the minority carriers will move towards the PN junction. And because of this movement of the minority carriers, there develops a leakage current, which is also known as a dark current. So dark current actually causes serious problems like it reduces the sensitivity of the device, it reduces the speed of the device. The dark current also depends on the series resistance connected to the photodiode. So we need to minimize the dark current. So actually what happens in a junction photodiode, when light falls in the P or N region, the electrons in the valence band will be raised to the conduction band and a hole is created in the valence band. So electrons or holes are created and these charge carriers, the electrons and holes, move in the material and this movement produces a photocurrent. And this photocurrent flows in the external circuit. So in addition to the dark current in a junction photodiode, we have a photocurrent also. Actually, the presence of dark current causes various problems in the proper functioning of the junction photodiode. So we can minimize the dark current by varying the ambient temperature or by varying the resistance value of the series resistor or by varying the reverse potential. Now, this is the typical IV characteristic of a photodiode. These are the uses of a photodiode. It is used in disc players, smoke detectors, pulse oximeters. So various applications are there for a junction photodiode. Next is a pin photodiode. It is positive intrinsic negative photodiode. This is the block diagram of a pin photodiode. Here we will introduce an intrinsic semiconductor layer in between the P and N regions. And this intrinsic layer is having a very large width and it is lightly dotted. So what happens when light falls on the material? When light falls on the material, again electrons are ejected from the valence band to the conduction band and electron hole pairs will be created. And here a large number of electron hole pairs will be created because of the large width of the intrinsic layer. Even if it is lightly doped, we'll be having a large number of electron hole pairs here because of the large width of the intrinsic layer. So there is large photocurrent. The large photocurrent will increase the efficiency, will increase the sensitivity, and will increase the speed of operation. So these are the advantages of pin photodiode over a junction photodiode. And it is suitable for attenuators, fast switches, photo detection, and high power applications. This is the IV characteristic of a pin photodiode. Next is an avalanche photodiode. It is a very sophisticated photodiode. Here, in addition to the normal electron hole pair creation and photocurrent generation, we have an internal gain mechanism. So, this avalanche photodiode includes an internal gain mechanism to amplify the photocurrent generated in the detector. And this gain mechanism is similar to a photomultiplier tube, but the avalanche gain is lower than that of a photomultiplier tube here. So this is the block diagram of a pin photodiode and the plot of electric field versus distance. So here, when light falls on this material on the depletion region, electrons will be ejected from the valence band to the conduction band, and electron hole pairs will be created. And these electron hole pairs will move or will be accelerated with a high electric field at the depletion region. So because of the high electric field at the electric force at the junction, the charge carriers will be accelerated and it will move with high kinetic energy. The charge carriers moving with very high kinetic energy can collide with neutral atoms in the crystal, and it will cause the electron hole pair creation. Because of the collision with the neutral atoms, the electron will be emitted or will get free from the neutral atoms, and it will create a hole in the valence band. So more and more electron hole pairs will be created because of the accelerated charge carriers, and that will increase the photocurrent. So the electron hole pairs created because of the accelerated charge carriers are known as secondary electron hole pairs. And the production of secondary electron hole pairs is known as impact ionization. Impact ionization. So this process is the electron hole pair creation due to the accelerated charge carriers. The production of the secondary electron hole pairs is known as impact ionization. So in this way, we can get more and more photocurrent So an avalanche of photocurrent is produced. So the internal gain mechanism here is known as the avalanche current multiplication. So in an avalanche photodiode, we have an internal gain mechanism known as the avalanche current multiplication. This avalanche photodiode is used in various applications like optical communications, aerospace applications, particle detectors, etc. Now, phototransistor. Phototransistor converts light energy into optical energy, and it is made of a semiconductive material and which is encased in a transparent cover, because light has to fall on the sensitive part of the phototransistor. So it is encased in a transparent cover, and this phototransistor is similar to a conventional transistor. It is also having three terminals like emitter, base, collector, etc. Emitter, base, and collector. In a conventional diode, the base region is very thin, but in a phototransistor, the base and collector regions are very thick. The base of the transistor amplifies the light incident on it. So in a phototransistor, the light is incident on the base region of the transistor. And that light produces a high current and it goes to the emitter circuit. And a voltage is developed. So this is a phototransistor. The base region and collector region are very thick. This is the circuit symbol. This is emitter region, collector, and base. Actually, this is the circuit symbol of a conventional transistor. The phototransistor can be represented like this. So this is the circuit symbol, a normal circuit symbol of a transistor with two incoming arrows. Represents a phototransistor. A phototransistor has a very high current gain. It is sensitive than a photodiode. When light falls on the base region, a current is developed. It goes to the emitter region, and this current will get amplified due to the normal transistor action. And it is having a very high current gain. It is sensitive than a photodiode and lower level of noise. Next is solar cell. Solar cells converts solar light energy into electricity. So it converts sunlight into electricity. It is a heavily doped PN junction diode. It is similar to a normal diode, but it is having a very large area. So we can call solar cell as a large area diode, a large area photodiode. It is having an anti-reflection coating in order to reduce the light loss from reflection. Now, in a solar cell, this is the typical IV characteristics. The blue line represents the power versus voltage, and the red curve represents the IV characteristics of a solar cell. Now, from the IV characteristics, we can calculate the fill factor and the efficiency, the conversion efficiency. So fill factor is actually a measure of the shape of the IV characteristics. Or we can characterize a solar cell based on the open circuit voltage, short circuit current, fill factor, efficiency, etc. From the IV characteristics, you can have open circuit voltage here at VOC. The current value is 0. So open circuit voltage is the voltage across a solar cell when the current across it is 0. And the short circuit current is the current across a solar cell when the voltage across it is 0. So from these values, we can calculate fill factor as P max divided by VOC into ISE. P max is the maximum power point. A solar cell has to be operated at maximum power point conditions in order to have a maximum power output. So the maximum power point corresponding to the P max, you can obtain VMP. The voltage corresponding to the maximum power point is VMP and the current is IMP. Now the conversion efficiency, eta, is equal to P max divided by the input irradiance into area of the solar cell. So by knowing these values, VOC, ISC, fill factor, etc., we can characterize a solar cell in research. So in this video, we have seen, we dealt with so many optoelectronic devices. Hope that you enjoyed it. Thank you.